In this and the next two videos, we'll talk about sensitivity analysis for linear programming based on our Blue Ridge example. We'll look at the sensitivity report for the Blue Ridge example and explain what each number means and how we get each of these numbers. We'll also demonstrate how we can use the information in the sensitivity report to answer some practical and interesting questions. The key reason why we want to conduct sensitivity analysis is that those input numbers are largely estimates. There's no guarantee that these numbers will be what we have estimated or assumed. So it is important to ask and answer questions like this. What if the unit profit of Aquaspar is $400 or $325 instead of $350? What if there are 180 pounds instead of 200? Sensitivity analysis tries to answer some of these what-if questions. Let's take a look at the sensitivity report of the Blue Ridge example first. This is what the sensitivity report of Blue Ridge example looks like. For the most part, it's pretty straightforward. In D column, we have some final values, such as 122 aquaspars, 78 hydrolysis, that is our optimal solution. And final values for constraints, we used 200 pounds, 1566 hours of labor, and 27 12 feet of tubing. And in F column, we have some existing information. For example, objective coefficients for Aquaspar and Hydrolux are $350 and $300 respectively. And right-hand side values for the constraints are 200, 1566, and 2880 respectively. In this video, we are going to talk about allowable increase and allowable decrease with respect to objective coefficient. In the next video, we are going to discuss shadow prices and their allowable increases and decreases. In the last video on sensitivity analysis, we are going to focus on the reduced cost. One of the what-if questions we asked earlier is, what if the unit profit of Aquaspar is $325 instead of $350? How are we going to answer a question like that? And we can do that using the information from the sensitivity report. First of all, the new unit profit of Aquaspar is $325. That is a decrease of $25 from the original unit profit of $350. And then let's take a look at the allowable decrease. In this case, it is $50. The actual decrease, 25, allowable decrease 50, 25 is of course less than 50, and our conclusion is the optimal solution will remain the same, that is 122 and 78. And then we can calculate the new profit accordingly. That is going to be 122 times 325 instead of 350 plus 78 times 300, which is $63,050. The net impact of such a change is going to be a loss in profit. The loss will be 122 times 25, which is $3,050. To sum it up, this is how we use allowable increase and allowable decrease associated with objective coefficient. If an increase in the objective coefficient is no more than its allowable increase, assuming everything else being the same, then the original optimal solution remains to be optimal. Similarly, if an actual decrease in objective coefficient is no more than its allowable decrease, assuming everything else being the same, then the original solution remains to be optimal as well. Now let me ask you a question. What if the actual increase or actual decrease is equal to the allowable increase or the allowable decrease? What would be your answer? Next, let's look at how we found those numbers for allowable increases and allowable decreases. To that end, we are going to turn to a pretty nice graph for our Blue Ridge example. This graph is the reason why I use this example instead of the example from our textbook. And you see the graph over here shows our feasible region along with all the boundary lines and the level curve. Let's take a look. This red line is the boundary line of pump constraint. And what about this purplish line? That is the boundary line of labor constraint. Lastly, this orange line is the boundary line of tubing constraint. And this shaded area in blue is our feasible region. Let's look at this blue dotted line. This is the level curve, and actually a special level curve, which gives us the optimal solution. Where can we find the optimal solution? On this graph, that is this green dot, and that gives us 122 and 78. Earlier, we asked and answered the question, what if the unit profit of Aquaspar is $325? Let's demonstrate that in this graph over here. What I'm going to do is to reduce the unit profit of Aquaspar from $350 down to $325 or even $300. And I would like you to pay attention to a few things. First, what will be happening to the level curve? What about the optimal solution, this green dot? And what about our feasible region? Let's give it a try. I'm going to decrease the unit profit of Aquaspar from $350 down to $345, $340, $335, $330, $325. When we are reducing the unit profit of Aquaspar, well, the feasible region stays the same. The optimal solution, the green dot, stays the same as well. What's happening? It's happening to the level curve. You will notice the level curve is rotating counterclockwise around the optimal solution. So far, the actual decrease is $25 from $350 to $325, which is still small. By that we mean the optimal solution does not change at all. Now let's keep making unit profit of Aquaspar smaller and smaller and see what happens. 320, 315, 310, 305, 300. Now what happened? Instead of having one green dot, we have a green line segment. You will notice at this moment the level curve is identical to our pump constraint boundary line. When the unit profit of Aquaspar is also $300, the original optimal solution, $122.78, remains to be optimal, but it is no longer the unique optimal solution. As you probably see over here, another optimal solution is $80.120. As a matter of fact, any point on this line segment will be also optimal. This is the case we call alternate or multiple optimal solutions. To sum it up, when we decrease the unit profit of Aquaspar until it reaches 300, the optimal solution remains the same, that is $122.78. If the actual decrease is more than 50, then chances are we are going to have new optimal solution. But that's exactly how we found our allowable decrease for Aquaspar's unit profit. It was 350, and we can decrease this number all the way down to 300 without changing the optimal solution. So the allowable decrease for Aquaspar's coefficient is 50. But there's another way of calculating this allowable decrease. Notice that at this point, this level curve is identical to the pump boundary line. That is to say, the slope of level curve is equal to the slope of boundary line of pump constraint. And that's how we can find the allowable decrease for Aquaspar's unit profit. Let's take a look at our PowerPoint. To calculate the allowable decrease of Aquaspar's unit profit, let's say the new Aquaspar's unit profit is X dollars. As a result, the slope of level curve will be negative X over 300. And we know that the slope will be equal to the slope of pump constraint boundary line, which is negative 1. So we have negative X over 300 equals negative 1. Solve this equation, we get that X is equal to 300. So the allowable decrease for Aquaspar's unit profit is going to be equal to 350 minus 300, which is $50. Similarly, we can find the allowable increase for Aquaspar's unit profit. Once again, let's assume that the new Aquaspar's unit profit is X. So the slope of the new level curve will be negative X divided by 300. And we can increase the Aquaspar's unit profit until the slope of level curve is equal to the slope of the labor constraints. Recall that the slope of the labor constraint is negative 3 over 2, and we solve the equation negative X over 300 equals negative 3 over 2, and get that X is equal to 450. As a result, the allowable increase of Aquaspar's unit profit is 450 minus 350, which is $100. Now, let's consider a more complex situation. Two or more objective coefficients have changed. In this situation, we can apply a rule named 100% rule. Simply put, if the total percentage change with respect to the allowable change is no more than 100%, then the optimal solution remains the same. Otherwise, we probably need to rerun solver to get new results. Let's see how it works in our Blue Ridge example. Suppose both Aquaspar and Hydrolaxis unit profits are different now. Both of them are $320. What impact does it have on our optimal profit? First of all, we see this is an actual decrease of $30 in Aquaspar's unit profit and an actual increase of $20 in Hydrolaxis unit profit. Second, the allowable decrease for Aquaspar's unit profit is $50. The allowable increase for Hydrolaxis unit profit is also $50. So the total percentage change with respect to the allowable change is 30 divided by 50 plus 20 divided by 50, which is equal to 1 or 100% exactly. That is to say, the optimal solution stays the same, 120 Aquaspars and 70 Hydrolaxis, still the optimal product mix. And we can easily compute the new profit. That is going to be 320 times 200, which is $64,000. The net impact will be a decrease in profit of $2,100.